Okay, everybody. So welcome to the PhD defense of Alex Padilla, who's standing here. So I'm Tom Weber. The rest of the committee is Larry Mayer sitting here, and then Neva Gupta, who is online, and Bill Waite from the USGS, who's also online, hopefully. And you're monitoring chats in case they can't hear or something like that, right? That's awesome. Thank you so much. So I'd just like to introduce Alex and then let her tell you about, she's going to obviously go through and talk about what she has done for her PhD, which is a piece of what she's done here. And just in terms of the logistics, so after she gives her talk, I think we'll open the floor up for questions from everybody, including the defense. I'd like for that to be as open as possible. And then we'll take a break and we'll excuse everybody, and we'll give people a chance to get up and use the restroom, whatever they need to do. And then the committee and Alex will reconvene here afterwards with Bill and Neva online. So just to let you know, that's what we're going to do this morning. So let me introduce Alex. It's my pleasure to do that. Alex came to us from the University of Puerto Rico. And actually, I think what happened is that she spent a summer at Woods Hole working there as a summer intern and somehow got her way up to UNH. And then I think we literally, or very close to literally, bumped into each other right there in the tank. And we had a conversation. And that led to Alex doing a couple of things. Well, she applied to UNH as a PhD student in ocean engineering and was happily accepted. But she also came with an NSF graduate research fellowship, a very prestigious fellowship. And so we were excited to have Alex anyway, but coming with that level of prestige was, I think, a fantastic thing. In her time here, she has done a lot of things, some of which she's going to tell you about, some of the things that, as with any graduate student, don't show up in the final presentation, but doesn't mean they didn't really work hard at it, and doesn't mean they didn't make great contributions there too. She's done lab work, a little bit of which you'll see. She's done some pretty intense numerical modeling on some pretty complicated physics problems associated with acoustics. She's done a lot of field work. She's worked off the coast of California. She's worked up in Alaska. She's gone to the Arctic. She's been around and she's done sort of the things that you should do as an ocean engineering PhD student. And I'm super proud of her for that. The other thing that she has really done is she's contributed a lot to the university. She's done just a lot of service. And I think that has been the Graduate Research Council. It's been through a number of different things. I think that Alex has been a go-to person from the graduate school in a number of different regards. And that sort of culminated recently with work that she and actually Liz here co-led on an URGE pod, the Unlearning Racism in the Geosciences. And they, several of us that are in this room were part of that. And I think that was a wonderful contribution with actions that came out of that are going to leave on. So she's done fantastic service to the university. She's, in the meantime, doing all of those things. She's developed this wonderful collaboration with the USGS and Bill Waite, who's part of our committee. And she's going to be leaving here this summer to go take a very prestigious Woods Hole postdoc. These are not easy things to get. And that's what Alex is doing. So I couldn't be more proud. And I think that maybe more generally, sort of in the tenure of a graduate student, there's this cycle you go through where maybe you come in and you're not really sure what to do or when to do it or how to do it. And so you come in sort of at that young graduate student level and you ramp up to the point where rather than asking what you can do or should do, you're now telling what you are doing and what you want to do and what you don't want to do as well, which is very important. And I think that transition is from a graduate student to a colleague and a friend. And that's the goal, right? And so I think that's where Alex is. She has this step here to get through and defend her defense on her way to becoming Dr. Padilla. And so with that, I think I'd like to turn it over to Alex, and I look forward to hearing what you have to say.
Thank you, Tom. I really appreciate that. And I really want to thank everyone for being here today in person and everyone online who's here to support me. As Tom mentioned, my name is Alexandra Padilla, and today I'll be talking to you about my thesis work, which is focused on understanding the physical properties of gas bubbles in the ocean and how does reality affect what we think we already know. In particular, I'll be talking about methane bubbles, but before that, I want to acknowledge, and I'm going to make sure that I can actually move my slides. Perfect. Before that, I want to acknowledge all the different funding sources that have funded my research. In addition, I want to thank my committee members for committing their time to be a part of this thesis, and also the many folks here at UNH and CCOM, the USGS Woods Hole Coastal Marine Science Center, and the University of California, Santa Barbara for all of the help during lab experiments, field work, and just the support that I've had throughout these 7 years as a PhD student. With that, we're going to talk about methane. Before we go into the ocean, I want to talk about methane in the atmosphere. As we know, methane is a greenhouse gas that contributes to climate change. And in 2018, the estimates of atmospheric methane concentration was approximately 2.6 times higher than it was by its pre-industrial equilibrium values measured in 1750. And this large increase in methane concentration in the atmosphere has led researchers to try to really understand the different source and sinks of methane into the atmosphere. One of these sources is methane from the ocean. And so methane released from the ocean has been studied for many decades, and it's widely distributed across the ocean seafloor. In particular, methane can be released in 2 different forms, as fluid gas and also as gas bubbles. But for the length of this talk, I'll be focusing on gas bubbles, mostly because it's my thesis, but also because bubbles facilitate the transport of methane through the water column itself. And so these gas bubbles are released in different type of plume morphologies and shapes and sizes. I just want to highlight a couple of those. First, we have what we call discrete columns. So these are individual bubbles that rise after each other in single repetitions. Often they have single sizes, but sometimes we get these more vigorous plumes, discrete columns that have a wide variety of bubble sizes. Sometimes we can have them spatially distributed along a line in the case of like bubble screens. And also within the water column, we can get these diffuse bubble clouds. And so these bubbles, as they rise through the water column, the methane within them dissolves into the water, becoming available for microbial consumption, which is then used through aerobic microbial consumption, which can lead to changes in the water column's geochemistry, causing oxygen loss and ocean acidification. But under certain circumstances, we can get situations where gas bubbles rise up into the upper water column and potentially up into the sea surface, emitting methane into the atmosphere. And so current estimates of atmospheric methane concentrations from the seafloor range from 1 to 13% of the total global budget. And this large variability has led researchers to really try to assess the environmental impacts from the contribution of methane from the seafloor in 2 different ways. One is by improving our capacity for long-term monitoring of methane flux from the seafloor, and the other is by improving the capacity to quantify methane flux and transport through the water column. And so in this thesis, we're going to investigate 2 different kind of prongs of these. One is by trying to understand how variations in bubble properties such as shape and size and surface coatings impact our capacity to measure gas flux in the ocean. And also we want to investigate the variability of methane flux released from the seafloor. And so the variability of methane flux has been studied for several years and is still an ongoing research topic. And both spatial and temporal variability have been hypothesized to be linked to tidal effects and also by earthquakes. In 2019, we went out to survey the Colloid Point Seep Field in Santa Barbara and compare them to different studies that have measured methane flux or gas flux in the ocean in that particular seep site. But due to different methodologies used to measure the gas flux in this particular region, it was difficult to try to assess whether the variability that was observed was because of temporal variability or because of different methodologies used. So other researchers such as Romer et al. And Ma et al. Have deployed long-term monitoring systems to be able to look at this long-term variability of methane flux in the ocean or just methane concentration in the water column itself. However, due to low resolution sampling, it becomes really difficult to attribute where these temporal variabilities are being caused by. And so objective 1 is focused on establishing a long-term monitoring system to investigate the variability of the natural methane seep sites itself. But how do we study methane bubbles in the ocean? We often use acoustic systems, and this is because the acoustic systems take advantage of the large acoustic impedance contrast that exists between the gas within the bubble and the water column itself. And this is what allows bubbles to be excellent scatterers in the ocean. And so often we use different type of acoustic systems such as single beams and multi-beam echo sounders because they allow us to map a very large distribution of these seep sites. But we've also used acoustic systems to invert for gas flux estimates using common acoustic conversion techniques. And these acoustic conversion techniques rely on analytical scattering models that tell us information about the bubble itself, and then we can invert for bubble size or shape, for bubble size or volume. And so to talk a little bit about those scattering models, they help us predict how a bubble scatters sound in the ocean. In particular, we're interested in sigma BS, which is the acoustic backscattering cross-section. And this parameter is a function of many properties of the bubble and the medium itself, such as the bubble size, the incident frequency of the acoustic system that's being used, and other physical properties of the medium of the gas. And so here's an example of what this looks like. So we have the acoustic backscattering cross-section for a 1 millimeter radius bubble as a function of frequency for 2 commonly used models for acoustic conversion techniques. And this curve is what we typically call the frequency response of the bubble. And so if we were to compare this with bubbles of 2 different sizes, a 2.5 and a 5 millimeter radius bubble, we can see that the frequency responses of each of these bubbles are quite unique. And this is what really allows us to infer bubble information in acoustic inversion techniques. However, these models assume that the bubbles are spherical in shape. And when we go out into the ocean and we go to study these bubbles, and studies such as Wang et al., when we look at the bubble size population, they tend to range between 1 and 10 millimeters in diameter. And when we look at visual evidence of these gas bubbles, they're not spherical in shape. They're wobbly or irregular. And in addition to this, as they rise through the water column, they wobble in space, and they also change their shape and their size as they rise. And so this violates one of the assumptions of these analytical scattering models, and therefore we're objective 2 is focused on understanding and quantifying the effect that bubble shape and size have on the acoustic backscatter of single gas bubbles. Some researchers have used and developed numerical models to help us understand what happens within the water column itself. So we can track the dissolution of gas bubbles in the ocean by looking at how they change in size as they rise, but also how the methane concentration within the bubble dissolves within the water column. And so this allows us to have a more synoptic view of what's actually happening in the water column with the acoustic measurements. Sometimes you can only see snapshots of what we're seeing in the ocean. And so these dissolution models, similar to the acoustic models, depend on several parameters of the bubble and the medium themselves, such as the bubble size and the area, the cross-sectional area, the mass transfer coefficient and rise velocity of the bubbles, the solubility limit of the water, and the initial concentration of gas within the water column itself. However, sometimes when we go out into the ocean in very high pressure and low temperature conditions, we can actually form what is known as a hydrate coating on the bubble surface itself. And this has been observed in field experiments and lab experiments and in nature. And they've been observed to reduce the dissolution rate of gas through the bubble itself as they rise through the water column. And this hydrate affects parameters such as the mass transfer coefficient and the rise velocity. And a lot of these dissolution models that we have been developed to track the fate and transport of methane in the ocean still don't quite take this into account or don't understand how the surface coating affects certain parameters such as the mass transfer coefficient or the rise velocity. And so what objective 3 is focused on is understanding and quantifying the effect that hydrate shell has on the rise velocity of single gas bubbles. And so hopefully together, the goals of these individual objectives will help understand the limitations of the methodologies that I've mentioned above and give us a better sense of how these variations in bubble shape and bubble size and physical properties affect the fate and transport of methane through the water column. So now we're going to go into the individual objectives. Objective 1 is, again, focus on establishing a long-term monitoring system to understand the variability of natural methane seeps. And to do this, we're going to go all the way to the West Coast in Santa Barbara to a fairly well-known seep site known as the Colloid Point Seep Field. This seep site is known to be one of the most prolific natural hydrocarbon seep sites in the world. And there's a reason for this. This is an area where active bubbling there. It's just pure methane and oil in your face. It's really active, shallow seep site. So a lot of what you see is methane and the oil coming up from the seafloor. And so what we've done, and should say that a lot of the spatial and temporal variability that's been observed in this region has been linked to, again, tides and also to offshore oil production. And so we went out in 2019 to go map the spatial distribution of the methane seeps in this area. And within the Colloid Point Seep Field, there's Platform Holly, which is a decommissioned oil platform. And we found this really large active methane activity that's just west of the platform itself. And because the platform is decommissioned, this presents us with an opportunity to actually deploy a monitoring system on the platform to monitor this westward plume activity. So what we ended up doing was mounting a split beam echo sounder onto a pen and tilt system that we can see here. And this pen and tilt system rotates the transducer to be able to map out this area of the plume itself. The transducer itself is mounted, so it's at a 15 degree angle facing the seafloor. In addition to that, the split beam echo sounder allows us to track the position of bubbles within the water column. And this will be important for how we study the seep activity in this area. And so just to highlight some of the data itself. So this is from the complete pen and tilt system. So it's completing a swath of the area. And so we have at about from 0 to 150 or so meters, we have the water column, which is all of this area right here. At around 150 meters, we have the return of the seafloor, again, because we're looking at the seafloor, the transducer is angled. And what we can see is this large area here. This is plume activity. And just to highlight the color bar is the acoustic scattering received from the transducer. And so we can see both spatial variability of the plume. We can see it moving around with probably currents and tides. But we can also see changes in the intensity, the acoustic return of the gas of the plume itself. And so we collect this type of data for about a month between September of 2019 and October 2019. But due to some malfunctions with the pen-and-tilt system itself, we had to fix the system in a direction just facing westward of the platform itself. And in this fixed position, we are able still to see both spatial and temporal variability of the plume itself in the data. And I'm just going to show you what this looks like, the complete record. So we collected this fixed mounted data from November 2019 all the way to December 2020. Again, we have the seafloor at about 150 meters below. And then within the water column itself, we can see this active acoustic scattering layer, which is the gas bubbles rising through the water column. And we can see, again, there's a lot of variability in space where the plume is, and also in changes of intensity. And we have this long-term time series record. And again, this is in acoustic measurements. And so what we're really interested in doing is converting this acoustic measurement of seepage activity into an actual volumetric gas flux measurement. And to do that, we really need to understand what kind of seeps we're seeing inside in our data itself, because it's really important to be able to account for volume if it's a cloud or area if it's a screen. So what we're going to do is talk about how we kind of did that. So here's just a couple of days, 3 days worth of data. Again, we have the acoustic time series, the echogram of the data itself. And we also have what's known as the alongship and the athwartship angles of the transducer. And this is what measures the position of targets within the acoustic beam of the transducer. And that acoustic beam here, we have a cross-section of what that looks like. So it's a circular beam in the cross-section, and the alongship angle is roughly in the vertical direction of the transducer. And then we have the athwartship, which is roughly the horizontal direction. And the reason why we want to look at this is because when we start looking at the phase angles, we can, or at the electrical, at the angles of the transducer, we can see structure in the positions that we're acquiring of the targets within the plume. And in other regions, we can see non-structure. And so we're going to look at these areas. So the first one is when in one angle, we have this linear phase ramp up of angle, and then the other, we have a constant angle. And what that looks like is single bubbles rising through the acoustic beam of the transducer as a discrete bubble column. Now, if we were to take this bubble column and spread in one direction, what that looks like in the angle data is in one of the directions, the angles will be random, while in the other direction, they'll be mostly constant. And now it looks like an array of discrete bubble columns that form a bubble screen. And now if we were to take that screen and spread it out in the other direction, in both angle directions, we get random angles. And what that looks like is more of a diffuse cloud. With the angle data, we're able to classify different plume morphology types that will allow us to take our acoustic measurement. And so we had to do this in an automatic way because we have a year worth of data and it would be really tiresome to go through manually. So what we did was we used the coherence factor. And this coherence factor measures the coherency between two different variables. In our case, we're looking at the coherency between in the along-ship direction and the athwart-ship direction. And when we calculate this coherency, we come up with these type of plots where we can see structure, where we observe structure in the angle data. And when we compare this to some threshold, we're able to say if the coherence factor is higher than some threshold value, then the target is coherent and localized within the cross-section of the beam. If it is below the threshold, it is incoherent and it's dispersed within the beam of the transducer. And so now that we're able to identify different plume morphology types, we can use the appropriate equations to convert our estimates of acoustic measurements into estimates of gas flux. And I'm going to show what that looks like for one case. So this is for a bubble cloud. So we have the volumetric gas flow rate, which is Q, and this is the equation that we use to convert our acoustic estimates into gas flow rates. And so we have this term here. So SV is our volume backscattering cross section. So that's related to our acoustic measurements, the intensity of the plume itself within the volume of the transducer. We have this average sigma BS value, which is the average backscatter of a single gas bubble from the population of bubbles that we observe in the seep site. So this value, the sigma BS, depends on the bubble size distribution of the seep site. We have volume of the bubbles. We have this term here where UA is the rise velocity of individual gas bubbles and UP is any external rise velocity. So this is can be from affection from the bubbles itself or currents. NA is the bubble size distribution, and then we integrate all those values over the range of bubble sizes and the cross-sectional area that these plumes are intersecting. However, in Kohler Point C field, in particular in platform Hawley, we don't really have any information currently about the bubble size distribution. And so what we can report is an estimate of the normalized gas flow rate. So this normalized gas flow rate is basically our acoustic volume backscattering cross-section integrated over the area that the plume is intersecting. If we were to calculate if we had information about the bubble size distribution in the future and we wanted to calculate Q, we would be able to calculate it with this normalization constant. And it's important to note that UA, which is the rise velocity of single gas bubbles, and the acoustic backscattering, the average acoustic backscattering cross-section, these are also a function of the bubble size distribution itself. And often we use analytical models to fill in these parameters when we calculate the normalization constant. In other studies, other studies have been able to use measured estimates of rise velocity and backscatter, but when you don't have that, you can use analytical models. And so with that, we can report estimates of the normalized gas flow rates. And that's what I'm going to show you here. So this is for the sweep. So we have two different data sets. I'm going to talk about the sweep first. And so for one complete sweep, we can calculate one value of the normalized gas flow rate. And it's important to note that between each sweep, it's about an hour. So each sweep takes an hour to measure. And we can see actually a kind of a trend in the estimates of the normalized gas flow rates already. It's almost a fortnightly 2-week period. But what's really important and really interesting about this data set itself is when we start looking at the variability within days of measuring, we're able to see variations in the normalized gas flow rates that are on the order of magnitude. When we start looking at variability in the gas flow rates, the normalized gas flow rates within just a couple of hours of themselves, we can see that they vary by within a factor of an order of magnitude. And so this variability, because we're mapping the entire seep activity here, this variability that we're observing is likely caused by temporal external physical processes that are actively pumping or reducing the amount of gas coming from the seafloor itself. And we can look at the pyrospectral density function. So this allows us to look at what periods are dominant in our time series. And we can identify diurnal, semi-diurnal cycle periods, as well as an 8-hour period. And later, if we were able to collect external physical process time series, we could correlate these and say something about what might be causing this kind of variation. Moving on to the long-term time series, we have the black curve. So this is for the entire year-long record. The black curve is 10-second sampling intervals of the acoustic scattering, or that was obtained from the sampling of the transducer. It is the normalized gas flow rates. The red line is the daily averages of the measurements, and then the green dots are weekly averages. And then we can see from the data itself that there's a lot of variability, but because of what we've seen in the sweep data, we know that a lot of this variability is caused both by temporal variability of the release of methane from the seafloor, but also because of the spatial variability. So the plume is moving in and out of the field of view. Again, for this long-term time series, the transducer was fixed mounted. So a lot of the variability that we're seeing is just the movement of the plume within the transducer itself. But looking at the daily averages and the weekly averages, which hopefully dampen that spatial variability, we still see a lot of variations of the normalized gas flow rates that are within an order of magnitude. And also, one of the things is that we know is that it's really hard to see any seasonal changes in the data set itself. We only have a year worth of data. So if you want to say something more about what is occurring at monthly scales or seasonal scales, or even year or across the different years, we need to collect more data itself. We can look at, again, the pyrospectral density function. The black curve is for the entire record, for the black curve for the time series, and then the red curve is 30-day ensemble averages of the time series itself. We can see significant diurnal and semi-diurnal periods. However, it's difficult to correlate what's causing these variations because we don't have time series from external physical processes. And so with this, we were able to come up with a methodology that allows us to observe both spatial and temporal variability in the estimates of normalized volumetric gas flow rates. If in the future we have information about the both size distribution itself, we can take these measurements and calculate the total volumetric gas flow rate. In addition, I want to highlight that for those, we need to have more information about how gas bubbles rise through the water column and also how they scatter sound. And so the next two objectives focus exactly on that and will provide more insight on how we would actually calculate this normalization constant. So we're going to move on to objective 2. Again, it's focused on understanding and quantifying the effect that bubble shape and size have on the acoustic backscatter of single gas bubbles. And what we did for this objective was to compare experimental measurements of backscatter from single gas bubbles to several analytical scattering models that exist currently. So we have 4 different scattering models. So again, this is the acoustic backscattering cross-section as a function of frequency. And we have 4 different models that correspond to these models here. The red curves are analytical scattering models that assume that the bubble is spherical in shape. The black curve is a model that actually models the backscatter for oblate spheroids. And then also I want to highlight the fact that we have this Ka value. So we can also plot these frequency responses as a function of Ka. And Ka is just the ratio of the bubble size, the radius, to the acoustic wavelength that's being used. So what this means is it's how small is the bubble compared to acoustic wavelength. And the reason why this becomes important is because at Ka values that are quite small, below 0.1, all models do a pretty good job of predicting the backscatter. There aren't very differences between their individual curves. But as we start to increase either bubble size or the frequency that we're using to study these bubbles, the models begin to deviate from each other. And this deviation, when we start using acoustic inversion techniques, can create bias in our inversion for bubble size. And so what we did was we looked at 3 different bubbles. We generated 3 different types of bubbles: a small, pretty oblate spheroid bubble, and then a medium-sized bubble and a large bubble that were non-spherical and also wobbly in shape. And we insonified them with 3 different transducers over 3 different frequency bands: 8 to 20 kilohertz, 90 to 156 kilohertz, and 160 to 260 kilohertz. And this wide, broad range of frequencies allows us to look at the frequency response of gas bubbles in different regimes, in areas where Ka is small and all the models do a pretty similar job predicting backscatter, and also in regions where the models begin to deviate from each other, and we can start seeing effects due to bubble size and shape. So as we look, so this is one of the results from the study, from the experiment itself. So this is for the small bubble. We have the acoustic backscattering cross-section as a function of frequency. We have the 4 different models. And then we have our data, which are the gray dots, and where the 5th and 95th percentiles are represented by the error bars of our measurements. And so we can look at these similar plots for both the medium and the large bubbles. And I have an image of the bubble shapes so that you can see the differences between them. And I want to go through this and highlight the important regions of the data itself. So the first thing is to look at is for Ka values below 0.5. In general, no model is better at predicting the backscatter of the bubbles that we insonified in the experiment. As we start to increase, our frequency and look at the higher Ka value, so above 0.5, we can see that there's a large variation between the different scattering models, and also there's a large variation in the estimates for the larger bubbles itself. And so one thing to highlight is for the low frequency system, for the low frequencies, we see that all different bubbles have similar variability in their estimates, and we attribute this to the acoustic system itself. When we look at the higher frequency data, we can see that for the smaller bubbles, the variability in the estimates are quite low, except in certain regions like here. And the low variability is linked to the fact that as these bubbles rise, they're rising in a pretty constant shape. So they're not oscillating, not changing. And so their size is pretty consistent. So that allows us to have a very narrow error variability in our measurements. When we start looking at the larger bubbles, and as we've seen in the images and in the videos itself, because these bubbles, as they rise, are changing their shape, that starts to become a source of the large variability in the estimates of the backscatter we observe in our measurements. And with that, I want to highlight that when we start looking at the individual models in comparison to the data that we collect themselves, in general, across the wide band of frequency ranges and for the bubble sizes that we see, Both the Ainsley and Layton model and the Yee model are better predictors of bubble size using acoustic inversion techniques. And this is what allows us to look at, to better understand which models we want to use when we look at using these for acoustic inversion techniques. Moving on to the last objective, we have it's focused on understanding and quantifying the effect that hydrate shell has on the rise velocity of single gas bubbles. And similar to what we did for objective 2, we're going to compare rise velocity estimates of hydrate coated and non-hydrate coated gas bubbles to existing rise velocity parameterizations that exist in literature. In particular, these rise velocity parameterizations are some of the ones that are used in dissolution models that track the fate and transport of methane in the ocean. Another point to highlight is that all of these models assume that the environment itself is what we call contaminated, and this contamination assumes that the bubble surface is inhibited, so there's a reduction in the internal circulation within the bubble itself. And we use these models because it has been shown that in natural environments, there's enough surfactants and particles to inhibit the surface, causing it to be contaminated itself. And so what we did was we generated single gas bubbles in what is a flow loop device that we can see here. So this flow loop device functions with a circulation pump. It flows the water in a counterclockwise direction. And we use this pump to help regulate the temperature within the flow loop itself, and also to dissolve the gas of the gas bubbles that are released in the flow loop. When we actually do our measurements of rise velocity, the circulation pump is turned off so that the water is in a steady state quiescent state, so that when the bubbles rise, there isn't any external influence on the bubbles rising. We use a solenoid valve to inject single gas bubbles through an orifice needle. We use different sizes to create a wide range of bubble sizes. And then to image the bubbles themselves, we use 2 cameras that are placed perpendicular to each other. They were backlit with LED panels, and we used a diffuser to help diffuse the light. And now I'm just going to show you, what I'm going to do is highlight what kind of bubbles we actually made in our experiment itself. So we used 3 different gas types. We used air, we used methane, and we used xenon. And we use xenon in our experiments because it creates a similar hydrate structure that methane does, but at lower pressure temperature conditions, so that we can use our flow loop device. Our flow loop device is an acrylic system, so that we can actually image the bubbles. And so we released these gases in 3 different conditions. So air, methane, and xenon were released at room temperature and atmospheric pressure. Methane and xenon were released in room temperature and at a pressure of 1 megapascal. And then xenon was the only gas released at temperatures between 10 to 15 degrees Celsius and 1 megapascal of pressure. And that's because within this temperature range, pressure is where the hydrate is stable, so we can form stable hydrate, which is given by this curve here, which is known as the hydrate stability curve. And this is for xenon gas. And within this curve, everywhere within that curve to the left of that curve is where hydrate is stable. And so now I can actually show you the data itself. And so we collect 150 bubbles within our flow loop system, and we collected a whole suite of data. Just with the 2 images we can see here, camera 1 and camera 2, rise. Information about the trajectory of the gas bubble. Because we have 2 axes, we can actually map out the position within the flow loop and look at different trajectories, so helical, zigzag, or a straight trajectory path of these gas bubbles. And from and extract estimates of the rise velocity. So we can estimate the vertical rise velocity, which is given by the black dots, instantaneous vertical rise velocity. We can also estimate instantaneous total velocity. So this is looking at the vector position from the trajectory. And then we can fit a curve to this trajectory and look at the average rise velocity. And so with all of this data, we can start looking into a lot of the dynamics of bubbles as they rise through the water column. However, for the sake of time, I'm just going to focus on just the rise velocity estimates and also the comparison with the models. And so here we have a rise velocity of gas bubbles as a function of diameter, equivalent diameter, and also as aspect ratio, where the aspect ratio is just the ratio of the major axis to the minor axis. And we have two different types of bubbles, our non-hydrate coated bubbles for all the different gas types and release conditions. There wasn't any significant difference between the gas types or the different release conditions, so we were able to just plot them together. And then we have in red the rise velocity of hydrates. And then we have some examples of what some of these bubbles look like here on the bottom part of the plot. And so I just want to highlight a couple of regions. We can see that the hydrate gas bubbles in general tend to rise slower than their non-hydrate counterpart by about 10 to 15%. However, there are some regions where these hydrate gas bubbles are rising at a similar rise rate to gas bubbles of the same size that have no hydrate coating. And this is likely due to the shape of the bubble itself. So these bubbles tend to be more spherical in shape. And so that allows them to rise a little bit faster than shapes that have that are irregular. And also we can start to see some trends in the data where non-hydrate gas bubbles tend to rise faster as their aspect ratio increases. And also as the aspect ratio increases for hydrate coated bubbles, there tends to be a decrease in the velocity, the rise velocity. And this highlights how shape has an effect on the rise velocity based off of whether it has a coating or no coating. And finally, I want to highlight the comparison between the estimates that we observed in our measurements with the different models that exist. So we have the rise velocity as a function of bubble size on the top, and then we have the percent error between the measurement and the different models themselves. As we can see, so this is for just one type. So this is xenon released at pressure. And we can see that in general, at high bubble sizes, most of the models tend to do a pretty good job of predicting the rise velocity. However, the McGinnis model in general, for a broad range of bubble sizes, tends to produce the lowest error in the rise velocity estimates. Now, this again is only for the xenon bubble here, but we saw similar results for the different gas types and the different release conditions for non-hydrate coated bubbles. Now, when we look at hydrate coated bubbles, now we have to look at two things. So surface tension is an important parameter for a lot of these models. And in literature, and a lot of the dissolution models that we currently use, the surface tension that they use is the one of the water gas interface. And so when we use that surface tension, in general, the McGinnis model tends to produce the lowest error in rise velocity. But there is some literature on the estimates of surface tension of hydrate gas bubbles in hydrate gas bubbles. And as we can see in general, most of the models tend to produce relatively low errors. So from this, we can say that regardless of the surface tension and bubble size, the McGinnis model tends to produce the lowest errors in rise velocity estimates. This is important for when we start looking into using this to calculate our estimates of volumetric gas flow rates, but also in understanding which model can produce more accurate representation of rise velocity when we want to study the fate of these models. And so with that, I just want to summarize some of the outcomes from the individual objectives. Objective 1, we were able to establish a methodology for long-term high-resolution monitoring of gas flux in the ocean. And we were able to observe both spatial and temporal variations in the normalized volumetric gas flow rates. In objective 2, we're able to study the effect that bubble shape and size has on the acoustic backstory and cross-section, as well as provide some insight on gas flux quantification through acoustic inversion techniques. And also objective 3, we were able to look at the effect that hydrate has on bubble rise velocity and insight on which parameterizations represent bubble rise velocity accurately. And to kind of bring this all together, I want to come back to our estimates of our normalized gas flow rates that we collect in Santa Barbara, California. And this is for the sweep data. So this is the time series that looks at the entire plume site. And In addition, I've added values of the time series. This corresponds to the 5th percentile, 50th, and 95th percentile of the time series estimates that we have here. And coming back to these equations, we've looked at different rise velocity models. We've looked at different backscattering models throughout objectives 2 and 3. And there are different ways to describe our bubble size population. And so with the information that we know now, we can do a sensitivity study, but really for the sake of time, I'm really going to focus on the individual results obtained from objectives 2 and 3 and how we can use that to better understand platform hauling. And so by doing some digging, I found from Hornefeus et al. In 1999, they don't have a bubble size distribution themselves, but they report that they see bubble sizes that range from 1 to 15 millimeters in radius with an average bubble size of 6 millimeters. And so if we used a Rayleigh distribution, we can capture that variation in bubble size. And then using the results from objective 3, which is that the McGinnis model is the better predictor of rise velocity or produces the least amount of error in rise velocity. And we use the Ainsley-Layton model for acoustic backscatter. We can combine these 3 curves to calculate a normalization constant, which we can then use to calculate the total volumetric gas flow rate. And when we do that, we get estimates that range from 90 to about 1,200 meters cubed per second. And when we look at estimates that we collected in 2019, our highest or 95th percentile is within the same order of magnitude that we observed there. Again, it's important to highlight that in this seep site, when we look at our variability, it's really important to know that this kind of variability exists. It can change within an order of magnitude within what day you go out to survey the site. And so the results from this kind of sensitivity study using the results from objective 2 and 3 provide at least some insight on the methodology itself and a good comparison to previous estimates within this seep site. And so with that, I want to highlight the fact that throughout this talk, I've talked mostly about volumetric gas flow rate. But really what we're interested in is understanding the fate and transport of methane throughout the water column. And to do that, we need to have a better understanding of our dissolution models. And I've talked a little bit about the rise velocity, so we've talked about that, but there's still some parameters that still need to be further studied, such as the mass transfer coefficient and the solubility of gas within the water column. And in particular, understanding how surface coating affects these parameters, such as hydrate, which we've kind of touched briefly here, but also in the case of platform hauling, where there's a lot of oil mixed into the water column, into the release of the bubble in the seep site itself, understanding how surface coating from oil-coated bubbles is going to affect parameters such as the mass transfer coefficient rise velocity as well. And finally, because acoustics is very important to me, understanding how these surface coatings affect the scattering models, the scattering of gas bubbles as they rise through the water column. In particular, because if we're going to use these models to better predict our estimates using these normalized values, we really want to understand how they're affected by the different surface coatings. And some of these questions and research topics I'll be addressing during my postdoc that Tom mentioned, so it'll be very exciting. But before, so this is it. Sorry. But before we move on to questions, I know I've been talking for a while now, but there are a lot of things that I have to give now, and I want to spend some time doing that. First of all, I want to thank my first 2 mentors in ocean engineering, Silvia Rodriguez-Abudo and Anna Michelle. They provided me with my first experience in ocean engineering. They provided a lot of field work experience. They provided a lot of opportunities for me to explore my interests and supported me into going into grad school. Sylvia had a really big role to play when it came to coming here to UNH. She was already here. So it kind of made sense at that point. I also want to thank Diane Foster, and I want to thank Bill Waite for being mentors throughout the graduate career. Both of you have opened your homes to me, and I'm internally grateful for that. Not just providing academic support, but also just support throughout the whole process. And then there's Tom. I had worse pictures, so this is great. I'm actually very happy that you remember how we met, because that's exactly what I was gonna say. That was December 2013, right before I decided to go into ocean engineering to do the switch. And you were doing some experiments, and I happened to be getting a tour, and you kind of intervened, took hold kind of in the way that you do, walked me around CCOM, showed me all of the labs, and I feel like at that point I was just like, yeah, I'm sold. And you took a chance, and I'm really glad that you did, because I feel like I've grown a lot because of this experience. So thank you, Tom. And then I really want to thank all of my friends. There's a ton of people that I have met throughout the last 7 years that have formed a very integral part of my life and of my research. Try not to cry. I want to start with Jaleti, who's online. She's been my friend since undergrad. She's always been supportive, so I'm really grateful that she's here. There's Tina, Tiziana, all the JEPCO students who I've met throughout the years. Roxy, you've provided a lot of good people in my life, so thank you for that. You brought Max into that, so that's very important to me. There's Megan, Melissa, and Scott. You guys have been kind of like big siblings that have kind of helped alleviate a lot of the stress in the beginning years, and now are becoming more of colleagues as well. So friends and colleagues that I know I can rely on in the future. Because of COVID, I was able to go on Odin. Tom talked about this. I went up to the Arctic, and I met an excellent group of people there. And even within a short amount of time, they've kind of embedded themselves in my life. Julia, Clara, Salar, and Lena have been very supportive during the last stretch of this thesis, providing a lot of support, and I'm really grateful for that. And then, you know, Liz and Sam, you guys, I don't know what to say other than thank you. Andrea, you two have been very, very important in my life throughout the whole thing. So thank you for that. Just try not to cry. And then Lee Gray, Jinsey, you guys are new family at the USGS, and I'm really, really glad that I have a group of people who I can go to now when I finish. And finally, my family. My brother's online. I'm surprised that he wanted to join. I love him very much, but he has 2 kids, so I understand it's really early for him. So I'm really glad that he's here. Both of my parents are here with me today. It hasn't been easy. It's been a long 7 years. I know, as you can see, you shaking your head, Dad. But we did it. Lots of tears, lots of moments of happiness. So I'm really glad. I don't know what I would do without you guys. So now I've done it without tears, and I'm ready for questions.
Alex, I'm glad you ended that way. I think when we're doing our job right, we all do become a family, right? And I think that's a really important thing to acknowledge. That's why we're all here. So I think we can thank you, Alex, for that presentation. I think we can just open it up to to questions from all of us, including the committee. Can you just make sure that if there's somebody, Bill or anybody else online, or Neva or whoever else that you're
Bill and Neva should be able to unmute themselves. If anyone online has questions, either enter them in the chat or raise your hand, and Chris will give you privileges, or he will unmute you yourself.
I can start. Let me start by first reiterating everything that Tom said, and just congratulate you on just really a tour de force. I mean, academically, you've done theoretical work, lab work, field work. It's just remarkable. And we're all very, very proud, and also for all you've done beyond the academics in terms of really improving, I think, all of us in terms of social awareness. We appreciate that. Now, let me get to a question. I'm actually intrigued by this spatial temporal variation.
Yep.
And if you could throw up any one of those slides, 16, 17, 18, 19, all of them have amazing variations in there. And you looked at the spectral components of those. And
Yeah,
sort of
I'll
diurnal, semi-diurnal, diurnal variation. Yeah, that one's fine. The one couple before we even got it. I think 16 is the one I was intrigued with. And you kept saying, and clearly it relates to external processes. Certainly for those for diurnal or semi-diurnal, tide would be the obvious.
Yeah.
Is there not a tide gauge somewhere around Full Point that tidal forcing?
Yeah, there is. So in the Colo Points, the two tides, one is offshore, one is onshore. There is not a problem. So we can, and we have looked at it. That is something that is actually causing the effect, or to what degree each of them are contributing to that temporal variability.
Sounds like another thesis.
Oh, it sounds like a proposal.
Yeah.
That's what it sounds like.
But I'm even more intrigued with this kind of 2-week cyclicity, and that's a little harder, at least in my mind, to come up with an obvious forcing mechanism. What do you think about that?
I want to say it could be due to, I actually don't know. None of the time series that I looked at showed any fortnightly events. The only thing that I can really think about right now is if there's any seismic activity, like small seismic activity that might be doing something, but I'm not quite sure. I think there is, in the tide, there is a 13-day period, but it's pretty weak. So I'm not sure is my answer.
And this fortnightly periodicity is the most dominant one, that's true.
I don't know. Not that I can remember.
Can I follow up on that if you don't mind? I don't mean to interrupt you, but if you go to your time series for the year-long time series, in your power spectral density with that as well.
Oh, it's because it's not connected. That's why. This one? Or you're talking about the previous?
I thought there was another one. I guess that's it.
There's
but-
this one.
Yeah, okay. Yeah, no, it wasn't that. For some reason, I thought I saw a spike, not for the short time series, but for the longer one that had sort of monthly, a spike in basically, I don't know what it was, 30 or 40 days as well.
If
But
you-
it wasn't, I don't see it.
I mean-
don't see it there. Well,
Probably.
maybe that's it right there.
Yeah, it could be one of these peaks.
Yes, that's what I was looking at.
That's within the range of the error bar.
So that's, you think that's maybe just noise in your power spectral density estimate?
It could be, and the way to address that is by collecting more data. If we had several more months, another year of data, I think we can start to help resolve some of these peaks.
Can I follow up? If you go back to 7, I think slide 16. Right? Because the other thing I thought I was intrigued about was you talked about structure. One more. Okay. Yeah, absolutely. Any of those.
It's in the animation.
Oh, yeah, sorry, yeah. I think I can maybe
No,
stop.
it's okay. It's right. Just keep looking at this. And what you see is that during and this is against rain. So during what's varying is the range is coming in now. But during the far ranges, you get much more structure than you do during the near range. And you have a thought about what that is?
In the near range, our acoustic beam is much smaller, and so any fluctuation is just gonna it's gonna be there or it's not gonna be there. I think it's mostly attributed to the fact that the beam is smaller up in near.
Yeah, I think it's all geometry. You're getting at the appropriate beam angle, you're getting all kinds of response and yeah.
Just, and sorry, it's like, just that you mentioned sort of seismic activity, and it's a very seismically active place, I think, right? But you don't see these big, I would think that if that was a driver, you'd see big, episodic things. And maybe they're there, but if they're there, they're hidden to me.
I think look at whether they turn a generator on every 2 weeks on the rig or something like that.
Or there's something else going on. One of the things also is for this, we would have to be very lucky maybe to see, we're looking at a small area too. So if the earthquakes were gonna have some kind of contribution, I would want to look at it for entire sweeps so that we can make sure that we're seeing a full view of what's going on. Because it provides information, but it's still hard to decouple that spatial part. There's a ton of this.
So I had a question about the last thing you talked about, which was the C norm calculation.
Yeah.
So I think the second objective was the one where you were in the tank and you took pictures of bubbles and then you looked at their scattering as a function of frequency and the size. And when you calculate C norm, your mean bubble radius that you used from the Hornetvius, is 6, and then obviously it's falling off in terms of the distribution, but they're very large. Those are very big bubbles.
Yeah.
And I see in C norm you have 4/3 pi a cubed, which is an assumption that the bubbles are spheres. And so I'm wondering, I know that this isn't, I know like when you were in the tank, we saw those pictures of large bubbles at large Ka. And I imagine that those radii would be large Ka, and you wouldn't really have spherical bubbles, right? They wouldn't be spheres. And I was just wondering, if you could just comment on, do you think that you're, inducing a large amount of error by assuming they're spheres? Is there some way to deal with that? Because the size and the shape is clearly something that you've identified as being important.
Yeah.
Or does Ainsley and Layton, in your opinion, deal with that if you don't have to worry?
I think when it comes to the scattering, Ainsley and Layton, they don't take into account bubble shape or size, and in particular, they assume that K is quite small. That's one of their assumptions. But the way that their model works, it kind of, we can kind of look at, it does a really good job of predicting the average. For this term, for the volume term, we could look at how we could take this, right, and we can divide it, like when we look at rise velocity, curves in general, they have regimes. So you have a spherical regime, you have an ellipsoidal regime, and you have a kind of non-wobbly or irregular shape regime. That's something that might be able to be done with the C norm, where you can divide it into the different regimes and use, okay, well, in this area, it's spherical, so let's use a spherical volume. In this area, it's ellipsoidal oblate, let's use an appropriate volume for that and do a sensitivity study and actually look at what the errors are because of that. Volume does play a big role in this value.
Yeah, so you're cubing that.
Yes.
Right? So I'm just wondering if it, is it more important, do you think, than, using the correct model is to actually say, I'm pretty sure this bubble isn't actually a sphere.
I can answer that question. Did a sensitivity study. So we used 2 different bubble size distributions. We used a narrow bubble size and a more broad range bubble size distribution. We used 3 of the different scattering models, the Ainsley and Layton one is this dash one up here. And for the Ainsley and Layton model, for this sensitivity study, we see that, scattering has a very important contribution to it. Within just one bubble size distribution, you can be off by, orders of magnitude, depending on which analytical scattering model you're using. But also when we start looking at when we look at this term, this is the volume term. So that's this volume term. So when we look at the volume distribution of bubble sizes, definitely the volume contributes a very large portion of this normalized constant, which just means that we really need to understand the statistics of our bubble size distribution. Really know what the range of bubble sizes is.
Can I quickly follow up on that? For an irregularly shaped bubble, maybe bubble radius is on the large end, like where you're showing they're important. What do you even mean by bubble radius? Can you define what you mean by that? Because there's
Yeah.
not one, so there's a definition there.
Yeah, I would use the equivalent bubble radius, which is based off of a sphere of the same size. I would probably use that equivalent radius.
Which would give you the same volume in that C norm term. Wouldn't it?
Yeah, it would actually, yeah.
When you say sphere of the same size. is it-
By volume,
By volume.
by volume. Diane?
I think I have a poorly formed question. So as bubbles are rising through the water column or bubble plumes are rising through the water column, they are changing their diameter, they are changing their shape, they are changing their surface roughness, and they're changing their surfactants. And I'm sort of using surface roughness. I can imagine they could be
Surface ripples.
surface, exactly. And ultimately, you are taking some integrated estimate as you're interpreting this. So if you were to, and I think the surfactants get really interesting because that tells you something about water mass and what the surrounding environment is. So if you were to look at where the big unknowns and uncertainty are, where are they? And at what point could you then unravel all of that, invert all of that, and then say something about the overlying water masses? So could you eventually get to the point where if you said, I can nail this, the role of sphericity, and I could nail I know so much about this bubble, I know how wobbly and bubbly it is. Could you then use any of the variability to back out the surfactants in the water?
It's a good question. I don't know, because when we start thinking about gas bubbles in the ocean, when we go to study them, we're not really looking at them. So there's a lot of assumptions that go into that. And so if we did know, no, because a lot of the models for rise velocity, it's based off of whether it's a clean bubble, if it's a partially contaminated or contaminated. And what changes is the expressions of, for some models, it's the expression of the drag coefficient. But there is no direct relationship to the I might be mistaken. I just don't know a lot about this, but from my point of view, from what I've seen from the models that we're using now, there's no direct link between rise velocity and surfactant concentration. I know people have studied the effect of surfactant concentration on rise velocity. That's been studied here at UNH. But from the models that we use themselves to track the fate and transfer of methane bubbles in the ocean, those don't have a direct relationship to concentration. So with those models, I wouldn't be able to. But
hypothetically, one could.
Probably, maybe. That's a great NEVA question, I feel like. Who's done that?
I'll chime in there.
Oh, yes, you can. Can you turn up the volume?
I hope so.
Just give us a second. I can't hear well, but my volume is maxed. Oh, you can try and we can see if.
Okay. Can you hear me? Okay.
Yeah.
Is it okay?
Yep.
Okay. So I think with wobbly bubbles, it makes it extremely difficult. Even if it was steady bubble going in a single trajectory, I would say for clean, absolutely clean bubble, yes, you may be able to back out, provided you can see the shape. For completely covered with surfactant, possibly, but anything in between, because the distribution is now critical in terms of where the surfactant is accumulated, which depends on the shape and the velocity and so on and so forth. I think it would be hard to back calculate surfactant distribution or concentration. Does that sound reasonable?
It does, yes. It wasn't a question. She was just agreeing with you, I think.
Okay.
I have about 20 questions, but I'll stick to one or two. Could you go to the slide where you have Michael's model and so you know, one sort of, I mean, the understanding is that near resonance, the shape probably doesn't matter at all, which you should. Once you get on the tails, the shape is extremely important. So whether you're hitting it plate or edge is a factor. So that's just leading into the question that you state that Michael's model seems to fit better than Clay and Medwin. So I guess my question is, why is what do you think what assumptions is he making that makes it more correct than Clay and Medwin, or what is Clay getting wrong?
The difference between the two models, they have the same assumptions. The difference is how they describe the damping due to acoustic radiation. I might get this mixed up, and I think Clay and Medwin defines that the damping due to the acoustic radiation is proportional to the frequency. There is that it's inversely proportional. So that's where the differences lie between the two models. And because of the way that the backscattering is formulated, that allows the Ainsley and Layton model to have a higher backscatter compared to Clay and Medwin. So I think it comes from that damping term, mostly.
I think they're just lucky. Just so you know.
You think Michael's lucky?
Yeah, there's no reason why I should fit that.
Tom?
Thanks. Nicely done. Thank you. Appreciate that. I'm going to go back to slide 18. This is around these really fun time series that you were showing. And you were looking at some cross spectra and showing coherence.
Oh, yes.
That went by me fast.
This one, stuff.
The coherence 16, I think, or 18. I think it's 16 or 18.
This one?
Yeah, there you've got coherence. That's what you're showing in those color contour plots. So that's time on one axis and range on the other, and coherence. It went by fast. So what are the what's the frequency? What is it, the maximum coherence?
We're using, so we have the transducer that we're using as a broadband transducer. So we're just using the center frequency of the.
So that's the coherence at the center frequency.
Yep.
Did you look at the phase at all? Or did you look over the band? Like over the band, it's a finite band. As a function of frequency, you get a coherence, but you also get phase.
Yeah, I have not done that.
The reason I ask is I wonder if you can get velocity from that. Like you can get temporal time, you can get time rate of changes. I might be wrong. I'm just wondering if you can get velocity.
I'm not sure. I haven't done that. It's something that might provide more information about the systems itself, about the data itself, which might be beneficial for the future. It might be something worth.
Okay. That's good. Thank you.
Yeah, really nice work. This is a really hard problem. I've come at this from an optical attempt perspective, which I feel is much more simplistic than what you're doing with acoustics here. So when you're trying to measure normalized gas flow rates, right? The only way to calibrate your methods is if you know something about the flow rate, right? That's always what ties it back and makes it want to do. And it seemed like you formulated that in objective 1 with quite some good data, and then objective 2 and 3 try to get at what model to use and how to do this, and then you kind of came back and picked a model from some observational data. You got an average bubble size and said, okay, now I'm getting to these flow rates, right? Wouldn't it be maybe a bit easier to really need to tie this down if you just put some methane bubblers on the ocean floor and measured flow rate, and then just did this?
That would have been perfect.
The controlled experiment.
That would have been perfect, except COVID came.
Okay,
So, I mean, for our study in 2016, we did something like that. It was a mix of acoustic measurements with direct measurements of gas flow rates using our bubble capture device. So it's just an inverted funnel. We looked at the flow rate or the flux rate, and then we could correlate our acoustics to that and get an estimate. This is something that I think we really wanted to do, to go out and get a ground truth, right? And whether that's using optical devices or using a bubbler or catcher, but due to COVID and then time trying to finish, that was really difficult.
but that would be you putting something down that actually measures flow rate, and then you have your calibration
Yeah.
measurement that way. Great. So with one follow-up question, I found it, so I learned lots of things today, that on the 13% of the methane budget in the atmosphere comes from the ocean. With your model, how you tied this all up at the end, can you get get a better estimate of that number? Or is it?
I think from the results you can, so those estimates that I've mentioned are from machine learning, looking at different areas in the ocean and looking at what the potential is based on the spatial distribution. And I think by doing a sensitivity study and looking at the results that we have, I think we can potentially narrow that variability. But I think the problem ends up being is that we still don't understand how from site to site, how the temporal variability where we see order of magnitude changes is going to affect the total flux. And this is in the shallow sites. So shallow sites are really important, especially for atmospheric methane, because they can actually reach the surface. We're talking about deep methane sites. We don't really tend to focus on those when it comes to atmospheric methane, more on the water column part. I think that what I do think is that Platform Holly presents a really good study site to start looking into these large variabilities of different types of shallow plumes to get an even better understanding of what day-to-day variations is going to do to global, what that might change in global estimates. That's what I think.
Great.
Tracy?
Really nice talk. I always love the bubble. Yes. Yeah. I have a question about, so at the coal point, you have the sweep that you said takes about an hour.
Yeah.
Like, how much is a plume itself changing over that hour time scale? Like, what is the effect of that kind of, like, I always think of short scale time scale things.
I think that there is going to be an effect so I think within that hour, the plume is going to be moving around. But by capturing, and by the way that we actually estimate our estimates, we are gridding and we're correcting position based off where we see the targets within the plume. And so when we grid, as long as we actually capture the entire plume within that hour, we can be a little bit more relaxed about the smaller short-term changes because we're still capturing the entire plume. What could be done is doing more rapid. For each position, we did 10 pings, so maybe reducing that, which would reduce the time and seeing if there are any changes. Those are things that probably could be done to see what the effect of maybe these shorter times would have on the variability within our estimates itself too.
I was been trying to ask a question.
Sorry about.
That's all right. I have two questions, actually. My first one to this, and that is, when you talk about external forcing, tides and things like that on the time series of this, do you think that is modulating the process coming out of the seafloor or modulating your ability to measure that process? And if it's the process coming out of the seafloor, what do you think is the physical connection there?
I think it's the modulation of the seafloor, mostly because, again, with this sweep, if we were modulating our kind of our capability to find or to see them as they move, with the sweeper, we can actually track the entire plume. And the reason why I think it's because tidal forcings is there have been some studies in this area that have looked at it's a site called C10. So they had these kind of turbines collecting gas released on the seafloor, and they also observed this tidal component. And there probably is some relationship to pore pressure and high tide versus low tide, how much hydrostatic pressure is acting on those pores. So I think it might be linked to that. I would have to do more literature review to really understand the mechanisms.
The second question is about the coherence factor, and I might have this wrong, but I think that the result of that calculation is both, of course, dependent on the coherence of the two signals, but it's actually trying to measure, but the signal to noise of the signal itself. And you didn't mention that in the talk, but so do you like mask all the data before you do calculation to only capture the data that has a sufficiently high SNR before you try to measure its coherence, so that you don't assume something's incoherent, it actually is just a measure of nothing or background noise?
No, the coherence factor was, so the way that I used the coherence factor was to just identify, just even if it's background noise, if it's background noise, it should be, at my point of view, it should be incoherent. And so, so if it is background noise, then it's incoherent. But then what we do later is by looking at the acoustic intensity, that SNR, we take away anything that is background noise, that is below some acoustic threshold, and discard those. So then really, I hope I'm answering your question. I think hopefully that what we end up doing is, even if, even if there is background noise in our coherency estimates, we're not really using them in our data itself. But I might have understood your question wrong. So
I'm not sure I understand your answer, but I think I do, and I think you understood my question.
That's kind of incoherent, Val.
Yeah.
we both are. It's been a long day already.
So maybe, are you, okay, so maybe last questions.
Yeah, and just to follow up on that, I was curious what your threshold levels were for identifying not plumes, but bubble clouds, I guess, with coherency factors. Is that distinguishable significantly from background noise as opposed to like the straight columns, which are visible?
Well, so the coherency, the coherence factor, all it's saying is something that we see in the acoustic data, is it coherent in the plume or is it incoherent? So for a bubble cloud, both angles, so I'll just bring up a plot that is going to be maybe a little bit confusing, but hopefully not terribly so. So this is kind of what we get out from the coherence factor. So we get, for the different type of structures, discrete columns. This is another type of discrete column. We have our different screens, and then we have bubble clouds. So when a cloud exists, it's incoherent in both the horizontal and the vertical axis. And background noise will also have this incoherent structure. What allows us to differentiate between the cloud and the background noise, or something that's not coherent, is the fact that it has some acoustic threshold that it's exceeding. So it exceeds both some intensity, some acoustic intensity that we're measuring in comparison to regions where there is nothing. So if you look at our time series, for example, I'll just go back to the sweep, because that's really the easiest one to look at. When we look at the sweep, we have areas where there's really nothing going on in the data. So that would have incoherent, an incoherent coherence factor, or a really low coherence factor. And so when we use our thresholds, we're using this area where it's just background noise to distinguish. And then by comparing that coherence factor threshold and the acoustic threshold, then we can distinguish between noise and clouds that are going to be incoherent in both directions.
Alex, would it be fair to say that you sort of use the acoustic amplitude to do an initial detection, and then you use the coherency on those detections to classify it? Would that be fair?
Yes, that would actually be exactly what I did.
Okay. I think we should wrap it up. You have
One quick one, because all this discussion of noise made me wonder, has anybody just had a passive hydrophone here? Do these things make noise?
Yeah.
And I'm just wondering, if you compare the kind of the passive hydrophone results to the more quantitative active results, maybe you have an easy way to see what's going on.
That's certainly a thing. I know, and people have done this. Tim Layton's group in Southampton have done various versions of this. Preston Wilson has some experiments on passive acoustics. The problem is, maybe in Piccolo Point, it wouldn't be a problem because I don't think there's a lot of biology going around in that area, like stuff like that. I don't know, that could be because you have to be at the release point. So once they close, that's when you start hearing that's where you get your acoustic response with the passive acoustics. So that could be something that to link both of them would be interesting to do too.
That's a good question. I think Preston is actually, at least before COVID, was interested in actually doing just that at this very site.
Yep.
And people also use passive acoustics to go look for leaks
Yep.
underwater as well. So
I'm just thinking it's a way to much broadly monitor what's going on. If you have this real focused quantitative thing that you can compare to that. You might have a lot of insight.
And from the passive, you're probably, if you have a really broad passive hydrophone, then you could probably do bubble size distribution calculations as well, which would be really helpful for what we're doing too.
we have a data set from New Zealand if you're interested.
I'm not doing this weekend.
There you go. All right, I think we should wrap it up there. Thank you. Maybe we'll take a short break, just so people can stand up and we'll for attending.